So let's take a look at urine formation. So there's three parts to urine formation. One part is glomerular filtration, which is shown here. Next is tubular reabsorption, shown with those two arrows. And lastly is tubular reabsorption, shown with that arrow. So let's take a look at glomerular filtration. This is a process by which blood pressure forces liquid through the glomerulus and into the glomerular capsule. All right, so if we go back to this picture, here we're going to force liquid through the glomerulus and into that Bowman's capsule. All right, so the filtrate, this is a fluid filtered from the glomerulus and captured in the glomerular capsule. So the glomerulus is a really good filter here. Its filtration membrane is very large. You can see we have a bunch of small little blood vessels, which increases the surface area. And it's 1,000 times more permeable to water and solids than regular capillaries. The glomerular blood pressure is very high. It's about 55 millimeters of mercury, which doesn't mean a whole lot unless you compare it to regular capillaries, which are 18 millimeters of mercury there in pressure. So it's about 3 times higher pressure in the glomerulus than what's found in regular capillaries. All right? Like regular capillaries, plasma proteins and blood cells remain in the blood and are not in the filtrate. They can't be too big to be moved through. One of the problems, as I mentioned with the glomerulus, it is that it is just size selective though. So let's look at the filtration pressures here. So let's take a look at this picture here. So these arrows are trying to show what these pressures are. So let's take a look at net filtration pressure. So the first is glomerular capillary pressure, which we see here. All right, and that's going to force substances through the glomerular capillaries into the capsule. All right, so that high hydrostatic pressure forces stuff in that direction. Now this is opposed by blood colloidal pressure right here, trying to show there. And this is where plasma proteins exert osmotic pressure within the capsule. Okay, so we still have plasma proteins in here, and they're going to exert some osmotic pressure, pulling water back into the blood vessels. All right. Lastly is capsular hydrostatic pressure, trying to show here. All right, and this is water pressure within the capsule. You can kind of think about this like if you have a funnel and you start pouring water into the funnel, well, only so much water can go into that funnel at a certain time before it overfills because the opening, all right, here is small, right? So if we put a lot of filtrate in here, it's just going to push back some, all right? But even so, that glomerular capillary pressure wins overall, and we get about 10 millimeters of mercury pushing fluid into that direction. If we look at our glomerular filtration rate, or the GFR, this is a volume of filtrate formed each minute by the kidneys. So this is anywhere from 120 to 125 milliliters per minute, which equals about 180 liters per day that we're going to force through there. Now, if we think about, we have 5 liters of blood, 55% of our blood is plasma, so roughly about 3 liters of our blood is plasma. And so we filter our plasma about 60 times per day. So, but only 1% of that is excreted as urine, obviously. So, so that makes 1.8 liters per day is what we urinate out. Because if we urinated out all of this stuff, we would just be constantly drinking water and urinating all the time. All right? So a drop of only 15% in net filtration pressure stops filtration altogether, though. So this is why blood pressure is very important here when it comes to the functions of the kidneys. So an increase in blood pressure is going to increase our glomerular filtration rate. Dehydration will also will have the opposite effect. So it'll decrease our arterial blood pressure, and so that will inhibit filtration from occurring. Let's look at regulation of that glomerular filtration rate. This is important because if too much filtrate is put through, it will go through the tubules too quickly, and a lot of our needed substances will be lost as urine. We won't get them back. If it's working too slowly, we can reabsorb way too much. So, we need to give some time for stuff to go through that tubule so we can reabsorb it. But if we have too much time, we're going to reabsorb too many metabolic waste back. All right? So, let's look at some intrinsic controls. So, intrinsic, within the organ. So, this is known as renal autoregulation. So here the kidney maintains a constant glomerular filtration rate despite changes in systemic blood pressure. So let's look at the myogenic mechanism. So let's go back to this picture here. So here in the myogenic mechanism, smooth muscle contracts when stretched. So if we have an increase in blood pressure, that's going to stretch the afferent arteriole, and it will constrict in response to that contraction. All right? So if we stretch that afferent arteriole, it will constrict in response to that, and that's going to decrease the amount of fluid going into the capillary, and so that's going to decrease the glomerular capillary pressure. If we have a decrease in blood pressure, all right, the afferent arteriole will dilate. So by dilating, it's actually allowing more fluid to go into the glomerulus, so that's going to increase glomerular capillary pressure. We also have what is known as a tubuloglomerular feedback mechanism. So this is directed by the macula densa cells, so right there, all right? So if there is a slow flowing filtrate, or the filtrate is low in osmolality, which is essentially solid concentration. All right, so what I'm saying here is, if we come back here, if the flow through the tubules is either low, or the filtrate has a low concentration of solids in there, what we're going to do here is we're going to cause vasodilation of the afferent arteriole, and that'll push more blood into the glomerulus, right? We'll have higher glomerular filtration pressure, forcing more filtrate production, all right? If we have a fast flow or high osmolality, all right, so we have a lot of dissolved solids, we're going to get vasoconstriction. So we're going to constrict that afferent arteriole, reducing flow into the glomerulus, slowing that glomerular filtration rate. Some extrinsic controls involved here. One is the sympathetic division of our autonomic nervous system. Remember the 4 F systems, all right? So this controls our body's response to stress, right? So this causes the secretion of norepinephrine, and by doing that, that results in a constriction of the afferent arteriole. So that will constrict, all right? And that's going to reduce our filtration formation. Next is the renin-angiotensin system. So here, if systemic blood pressure drops, right, those juxtaglomerular cells there are going to secrete renin into the blood. Renin is going to decompose a plasma protein known as angiotensinogen. So angiotensinogen is converted into angiotensin 1. Angiotensin 1 then goes to our lungs and is converted into angiotensin 2 by those type 1 pneumocytes that we talk about in the respiratory system. Now, so angiotensin 1 binds to the ACE2 proteins there, which coincidentally enough are in the news because that's what the coronavirus attaches to as well. Anyway, so once angiotensin 1 goes to the lungs, it gets converted to angiotensin 2. Angiotensin 2 by itself is a vasoconstrictor, so that's going to make our blood pressure increase, all right, our systemic blood pressure increase. Angiotensin 2 also causes the afferent arteriole over here to vasoconstrict, so that backs up more fluid within the glomerulus, and that's going to increase glomerular capillary pressure. Angiotensin 2 also goes to adrenal cortex and causes the secretion of a hormone known as aldosterone. Aldosterone causes our renal tubules to reabsorb more sodium ions. And if we reabsorb more sodium ions, we're going to reabsorb more water. And so by retaining more water in our body, that's going to increase our blood pressure. All right, so long things that the renin-angiotensin system does there. Next is atrial natriuretic hormone, or ANH. So this is created by the heart when the atria overfills. So that's caused by having high systemic blood pressure. And so what atrial natriuretic hormone does is it causes our kidneys to excrete more sodium. And if we excrete more sodium, we excrete more water, all right? And so by having a lower water volume in our body, that's going to lower our blood pressure.